Hello everyone, welcome to Medicine 2020. I'm Dr. Shanmukh here. So today is a small topic of discussion which is very important and a little tough to understand for most of us, but let us make it so simple. That is flow volume loop curves. There are four component, four components here. Okay, flow, volume, loop, and curves. Right. So here you can say by seeing this that it's a graph plotted, okay, but how is it obtained? It is obtained by basic or simple spirometry. Okay, simple spirometry. So what do we obtain here? We obtain from here volume and flow. So how does the graph look? It is a graph is a curve, right? It's a curve. So there is this starting point. Okay, as you can see, it is starting here, moving in this direction, and again coming back to the same point. What do you call such a graph or anything that starts from one place and ends at the same place? You call it a loop. Fine. So this loop is based on deep inspiration and deep expiration. Deep or forced expiration. Okay, let us move forward. That being said, we are going to now discuss few things. So here, if you see the graph here, let us draw a separate graph. Okay, for this you want to plot velocity of air that is being expired forcibly. So you cannot interpret on the basis of velocity, so you are calculating it as liters per second. You cannot calculate kilometers per hour. In kilometers per hour air is blown out, so you are calculating it per liters per second, how much air is giving out per that you are breathing out per second on the y-axis. And on the x-axis, what are you doing? You're plotting volume. Okay, so the main component here is expiration. Okay, that is being on the positive side, the expiration. So if expiration is being done completely, it should reach a volume, you know. Okay, let us do that. So let us discuss the procedure before that. You ask the patient to take a deep breath, okay, deep inspiration, and that after that, you ask him to exhale forcefully into the spirometer. Okay, initially when the volume is very high, okay, the flow will be very high. So initial volume is high. That means it should be around some 6. Here, let us take it as 6 measure. The starting point as 6 liters. Okay. And the flow, it should taper as the time lapses. And it should become some value here. Okay. You cannot expire the entire air that is in the lungs. So you put the volume that is left after forced expiration as reserve volume, and here this one is total air that is expired forcefully, that comes under this curve. Okay, here you are inspiring again to fill the same amount of air that you have expired. Okay, so here you are doing a deep inspiration. Okay, this total point is this point. Okay, let us change the color. This point is TLC, that is total lung capacity. Okay, now moving forward, you can see that at one point you have very highest flow. Okay, you have a very high flow at that point is called peak expiratory flow rate, after which the graph gradually declines and reaches the baseline. Okay, after which the inspiration follows. After that, let us see what we can do with this information. There are two classes of diseases, right? What are they? Obstructive and restrictive. Obstructive and restrictive lung diseases. In center, we write normal. Here, what is happening? In the normal, you have this loop, right? This loop. In obstructive disease, what is happening? Where is the problem? It is with the expiration. Okay, if there is problem in expiration, the inspired air is getting trapped inside, okay, and not being expelled. So what happens here? Let us see. Let us draw the graph based on that. So this is, take this as 0, 2, 4, 6, 8, 10. Okay, for example, for instance, so whatever we do, we draw a normal here. Okay, this is, sorry, one second, give me, yeah. So this graph is normal. For, let us say, this is normal because you are having 8 liters, it is touching here, this is normal. So what happens in obstructive pathology? In obstructive diseases, the air is trapped. That means the reserve volume after expiration is increasing, right? Air is trapped. So what, after this, if you take an inspiration, the inspiration is normal, so it will go beyond the normal point, 10 liters. Okay, the, in expiration, the flow is obstructed. Do you think it will reach the normal? No. After which the PEFR decreases, and after which there is a small decline. See this graph, see this shape, this is called scalloping. Okay, this is called scalloping. So the inspiration also decreases because the amount of air that you take in, because of the excess reserve volume, it will also kind of, the depth will decrease, but the amount will increase. The total lung capacity will increase. Now you understand that in obstructive airway disease, the curve or the graph shifts to left. Okay, in restrictive, okay, let us see the restrictive airway disease. Okay, in restrictive, what happens? Let us draw it now. In restrictive, oh, this is too big. Okay, let us decrease this. Okay, in restrictive airway disease, what is happening? There is problem with both inspiration and expiration. Both we have problem, both are not normal. So what happens? Whatever amount of air that we take in also decreases, whatever we breathe out also decreases. See here, let us draw the normal. Okay, let us say that this is normal. So if the in everything decreases, the total lung capacities, all the lung capacities also decreases. So if this is 0, and let us take that this as blue. Okay, so the reserve volume also decreases. It is somewhere here. Okay, this is reserve volume. After inspiration decreased. Where do you think it will be? Around here, 6, and it was 8 here, right? It was 8 here, and this is 6. Okay, inspiration decreases as well as the expiration, and so does the PEFR, right? So this total capacities will decrease and this loop will shift towards right side. So R, R, right loop, restrictive, and an example is fibrosis, fibrosis. Okay, lung fibrosis you can say. Okay, RRR. And there is another curve which we will see here. Okay, see this. This looks like a box. This looks like a box. What is happening? See the normal TLC, normal RV, and post expiratory volume is also normal, but you see the depth, the flow rate decreased in both expiration and inspiration. In expiration you can see that there is a plateau like thing. Okay, so it says that the lung per se is normal. Okay, but there is something problem in the airway is not normal. It indicates, this box like graph indicates that it is a what do you say, airway obstruction for both inspiration and expiration. Okay, the whole graph that gives you a clue is, see, the y-axis is fine as usual, right? The y-axis 0, 2.5, 5, 7.5, 10. But here on x-axis you see the volumes decreasing from left to right, which is opposite to the conventional, okay, conventional graph. Apart from this, if you want to differentiate between FEV1 and this graph, in FEV1 and FVV2 V3 graph, what happens, it is expiration. Okay, expiration, that is flow plotted against time, one first second, second second, and the third second. Okay, this is FEV1, this is FEV2, and this is FEV3. This should be more than 75 to 80%. This should be 95% around. This should be 100. So if the time is moving on the x-axis, it will be 1, 2, 3, and 4. Okay, this is how you differentiate between the FEV and FVC curve versus the flow volume curves. Okay, I hope you understood how it is diagnosed and calculated based on the graph. Thank you very much. We'll see with the next small concept soon.